Hello, guys, it's me again, Rich Andre, and I'm going to be explaining the three laws of thermodynamics. Okay, so we first have to understand. Okay, let's first define thermodynamics. What is thermodynamics? Okay, it's basically just a study wherein it studies the relationship of heat to other forms of energy, like, for example, chemical energy, and so much more. Okay, so let's first go on to the first law of thermodynamics, which is also called the law of conservation of energy. The first law is that energy cannot be created or destroyed. Okay, and how I want to simply explain this is basically just okay. So let's say you have a certain energy. Let's just denote it as the letter E. This energy, okay, let's say let's say you let's say you burned down a house. Okay, let's say you burned down a house, just for an example. You burn down a house, and that house just turns to pieces of wood. Okay, burnt wood, a couple of ashes, and some cement blocks. Okay, so what the first law of thermodynamics basically just says is that this energy, okay, you can say that the house is the energy. Okay, it basically was not destroyed at all. Okay, before it burnt, okay, it was never really created. Like there was no origin to it. Okay, it just happened from certain parts of another thing that led to this house, and then consequently it burning. Okay, and the pile of rubble that um, you're left with afterwards, it wasn't really destroyed. It just happened to be converted, okay, into another form, if that makes sense. But that's the sort of premise of the first law, which is energy cannot be created or destroyed. Okay, so if you have an atom, okay, you can't create an atom. The atom is always there. Okay, the atom is always there. You can't create an atom. You can't destroy an atom neither. Like completely destroy it. You can't completely destroy an atom. You can't completely destroy anything. It just gets converted into something else. The form changes, but it's still not destroyed. Okay? So that's the first law of thermodynamics. Energy cannot be created or destroyed. Okay? Now the second law of thermodynamics, it says that for a spontaneous process, the entropy of the universe increases. So what does spontaneous process here refer to? Okay? It basically just refers to anything, any process that doesn't need outside help, that doesn't need, let's just say, OH, outside hub. Like for example, okay, an ice cube melting. You can't, okay, an ice cube naturally melting. Even without you tampering with the ice cube, okay, it's still going to melt, provided that the temperature is sufficient enough. Okay, still going to melt. Ice melting with just room temperature without any help at all is what we call a spontaneous process. Okay, so non-spontaneous process. There's also non-spontaneous processes. In these non-spontaneous processes, let's say that the ice cube hypothetically was melting at a temperature wherein it should not be melting. Like if it's cold enough to contain the ice cube, yes. If it's cold enough to contain the ice cube and the ice cube still melts, that is what we call, that is an example of what we call a spontaneous process. Okay. And no, I mean a non-spontaneous process. So we have, now let's go to the second part of the law, which is the entropy of the universe increases. So how I would simply explain what entropy means, okay? It's basically just the randomness or disorderliness or disorderliness of a certain system, okay? Okay? So you could say, let's have a box here. Let's have a little illustration here, okay? Let's say we have box 1, okay? So we have box 1 and box 2. Let's say that there are atoms there, okay? There are atoms. Both have 3 atoms, okay? And both have 3 atoms. Now I'm going to ask you a question. Which box do you think has more entropy? Okay? Provided that I already defined what entropy means, okay? I defined entropy as the randomness or disorderliness of a system. So knowing that, how do you figure out which of these 2 boxes have more and less entropy? Okay? Now, the answer will be box 2. Because box 2, okay, if you can observe from these poorly drawn atoms that I drew here, the atoms are much more far away from each other, okay? And the logic with that, okay, the logic with that is that when you have, okay, you can observe from these atoms that they have less space to work with. Okay, they have less space to work with because they're very close. The atoms are very close. Meanwhile, the atoms here, they're very, very far away from each other. So if we're just using logic to define, okay, entropy, this is more orderly because you can predict where the atoms are placed, okay? Because they don't take up that much space from the box. Meanwhile here, you don't really have a uniform sort of structure with the placement of the atoms inside the box, so that's why we consider it more disorderly. And so our answer for box 2 will be that this has more entropy. Okay, this has more entropy and this has less entropy. Okay, this has less entropy because there is a formal structure that you can sort of rely on. Okay, so for a spontaneous process, the entropy of the universe increases. Okay. So now that we know all that, okay, now that we know all this, we can just clearly define the second law as, let's go back to the ice. Okay, let's go back to the ice example. For a spontaneous process, this is a spontaneous process, the entropy of the universe increases. Okay, so the entropy of this particular object increases because now that the ice melted, okay, from my own understanding, instead of just having a solid ice, okay, which has, let's say, atoms that are very tightly placed, now you have loose kind of atoms just prancing around, and that makes it more disorderly, which goes back to entropy. Okay, the concept of entropy. The entropy increases in this specific case, okay, from my own understanding. So now that we're done with the second law, we can carefully proceed to the third law, which is the third and final law. The third law is a perfect crystal at 0 Kelvin has 0 entropy. Okay, so theoretically speaking, 0 Kelvin, okay, 0 Kelvin basically just says that there is this theoretical sort of absolute zero, okay, sort of absolute zero, okay, so this is the zero, okay, this is the number 0, this is absolute science, okay, so there's an absolute 0 temperature, okay, so a perfect crystal, okay, what they mean by this is any substance, okay, any substance that has no impurities, okay, it has no impurities, well, impurities, okay, impurities, that has no impurities, okay, so meaning there is no sort of flaws into the substance, okay, and that substance has everything just aligned, okay, everything just perfectly aligned on where they should be. And if you somehow manage to make that certain substance reach absolute 0 in Kelvin, okay, which is I believe the standard unit, one of the standard units for temperature. If you manage to make that substance reach absolute 0 in a perfect world, it will have 0 entropy. So there is less randomness or disorderliness in that specific substance. Okay? So that's basically it for the laws of thermodynamics. But I still I want to elaborate a little bit on the things that I know about entropy, okay? So we know that entropy is basically just the disorderliness or the randomness of a certain system, right? So entropy, okay, this is just an educated guess, okay, because I don't have that much knowledge on the topic, but I could say that the atoms, okay, or the molecules that are inside, let's say an ice, okay, let's say an ice cube again, the atoms more tightly packed, okay, more tightly packed, therefore there is less disorderliness, okay, they're more tightly packed, they're more predictable. But as soon as you melt, so let's say you melt this ice, right? Let's say you melt this ice. This is fire. Okay, so if you melt that ice, the ice is going to convert into just a puddle, and the atoms are going to be loose. Okay, the molecules or the atoms that are inside of the ice that were previously tightly packed and perfectly placed are more loose. Okay, and that's basically the idea of entropy, in my own understanding. Okay, so we also have heat. We also have heat, which is basically just the velocity. Okay, what we mean by velocity is just the speed. Okay, it's just the speed and direction of the molecules, the molecules that are inside a specific system. Like say this is fire. Okay, let's say that this is a fire, and inside the fire there are atoms in it. There are molecules, and those molecules, because the fire, you know, fire is basically a good source of heat. The atoms that are inside of fire, from my own understanding, will be faster. It will be faster in movement and more erratic, more erratic. Or maybe fire wasn't a good example. More like boiling. We could say we could just use the same example that we used here in a boiling pot of water. Inside the water would be molecules that are moving erratically in different directions, and certainly faster speeds than they would just being completely idle or being cold. That's basically what the laws of thermodynamics depict. So if you guys learned anything from this video, you can subscribe, give me a thumbs up. You can also give me feedback in the comments section below. If you like the video, you can say that. If you didn't like the video, you can give me your honest opinion where I should improve, so I can read it, and I'll definitely read it. So that's basically it for this video. If you guys enjoyed my video, you want to see more content like this, more long form content to get rid of your brain rot, you guys can just subscribe, and turn on those post notifications for new videos like this. Thank you guys for watching, and I'll see you guys in the next video. This is Rich Andre, signing off.